Compassionate, the Merciful, Engineering Plasticity, Chapter 2, Stress Analysis, Part 9. In this part, we are going to talk about deviatoric or reduced stresses. In the previous part, we introduced the idea of hydrostatic stress, and we said that sigma average, or the hydrostatic stress I1/3, is equal to that. If we consider again our doubly oblique plane, then this was the stress acting on this plane. And sigma average, the hydrostatic stress, the vector would be something like that, making equal angles to sigma 1, sigma 2, and sigma 3, while S does not make equal angles to these three axes. It makes angles alpha, beta, and gamma. If alpha, beta, and gamma are equal, then sigma average will be the same as S. But here is different. So sigma average is the stress vector which makes equal angles to all the three axes. Okay, then let's see what are the deviatoric or reduced stresses. Now, here again I have eliminated the plane. I have only two vectors here. One is S, is a general vector, and sigma average is the hydrostatic stress. Now we know that for any vector like S, we could have components. For instance, we could have one component along the hydrostatic direction, which is the hydrostatic component of stress, and one component is this one, which is perpendicular to this hydrostatic pressure. So we've got one component along this direction and one component perpendicular to it. Now S to the power of 2 is this one to the power of 2 plus this one to the power of 2. Okay? So what do we mean by deviatoric stress? We mean this vector. Okay? In other words, we have subtracted the hydrostatic component of the stress from the stress vector, and we are left out with the deviatoric or reduced stresses, as we say. It's reduced by the hydrostatic stress. So here is the hydrostatic stress or component. Now here are the reduced. Sigma xx prime is equal to sigma xx minus sigma average. So the components of this stress minus the hydrostatic stress give the components of the reduced stress, components of this stress. This one are this sigma xx prime, sigma yy prime, sigma zz prime. And for the sigma xy prime is equal to sigma xx, and sigma yz prime is equal to sigma zx, and sigma zx prime is equal to sigma z, because here we don't have any perpendicular components. All the components are the shear components. So we don't have any hydrostatic pressure which could be reduced from them, because they are themselves shear stresses, not any normal stress here, so that we could subtract the hydrostatic stress. Okay, because this hydrostatic stress, as we are shown here, are in terms of the normal components or the principal components, no shear stresses. So that's what we have here. Therefore, if we add up the sum of the reduced or deviatoric stresses are like this, and they are equal to 0, because sigma 1 minus that, sigma 2 minus that, sigma 3 minus that. if you add up all of this, it's become 0. So the sum of the deviatoric stresses is equal to 0. We are going to show this again in a little bit of time and see what are these components. So what is the use of this deviatoric or reduced stress? We are going to see how to use this. Okay then. Now in here we are showing the same thing that we showed in the previous slide in tensor notation. Okay, instead of sigma prime, we are showing S. So this S is the deviatoric stress, and this P is the hydrostatic stress. So the stress is equal to the deviatoric component plus hydrostatic component. Okay, so we are using tensor notations here. Instead of this Pij, we could write sigma m delta ij and Sij. So sigma ij, I and j could be x, y, and z, or could be 1, 2, and 3. Therefore, here we are saying, because in the previous slide we showed that for the normal stresses only we have reduced stress components, not for the shear stress. So if we write down this, we have to have when I is equal to j only, this component exists. Otherwise this component doesn't exist. So in order to accommodate that, we use this Kronecker delta, which says delta ij is equal to 1 if I is equal to j. So if I equal to j, we get only normal components, and then we have this hydrostatic component. But if I is not equal to j, then we have shear stresses, and this is 0. So this term becomes 0. Obviously, this is a mathematical notation. It's true for all the mathematical formulations. We have used it here for our convenience. Okay then. The spherical stress tensor is the tensor whose components are sigma m delta ij, where sigma m is the mean stress. See, this is we have only the components in the diagonal sigma m, and sigma ij delta ij is called spherical tensor notation because it has this stress applies on all over the body. Or otherwise we could write it like that. So these are just different notations, the same meanings as the previous slide. Okay. Also here we have another notation showing that the whole picture. Okay, sigma ij minus Pij, sigma ij minus sigma m delta ij, and in matrix form we can write these components as like that. And you see here in the diameter of the matrix we have sigma x, sigma y, sigma z. I have omitted because these are 2 digit or 1 digit, 2 indices or 1 index in the index. I have omitted the second one. Sometimes we write these like this. But here we mean sigma x, sigma y, sigma z. Okay, because we have sigma I, j, x, and y. So in here, delta ij is equal to 1, and in all other positions, delta ij is equal to 0 because I is not equal to j in here. Okay, so we get this matrix form also. Now substitute the deviatoric stress tensor in the main equation for the stress. So instead of writing it like that, we could write it like that: sigma ij equal to Sij plus Pij, because this is the hydrostatic component, this is the reduced stress, and this is the stress. So if we substitute for these sigma ij in here, and in here, then we get a different form for this equation, because as you remember, this I1, I2, I3, we called it I1 is this parenthesis, I2 is that one, and I3 is this one. We call them invariants. Okay, I1, I2, I3 are invariants. Now, if we change this, if we put instead of sigma xx, we put Sij plus the hydrostatic stress, then we get different equation, which is this. The resulting equation would be in terms of invariance of the deviatoric stress tensor as follows. So these are also invariants, but they are deviatoric stresses. Okay, so we show the deviatoric stress as S and the stress as sigma. Sometimes the deviatoric stress is shown as sigma prime, as I showed in the previous slides. Now let's see what we get. For instance, for J1, let us now obtain the invariance of the deviatoric stress tensor. We want to obtain J1, J2, J3. How do we do that? We will show that J1 is 0. Of course, we showed this in the previous slides, but we're going to show it again. So in here, we are going to write down sigma ij equal to Sij plus Pij, and sigma ij plus sigma m delta ij. And Sij, we can show here that Sij is sigma ij minus sigma m delta ij. So if we want to find these components, so we put here x, y, y, z, z, and similarly find that Sxx is sigma xx, sigma m, because I is equal to j, so delta is 1. So similarly, we could find components for Syy and Szz and put it here. Put these values in here. So if we substitute this, also remember that we had this component. So if we substitute for Sxx, Syy, Szz, we get sigma xx minus sigma m, sigma yy minus m, and sigma zz minus sigma m. Therefore, in here, we get sigma xx, yy, zz plus minus 3 sigma m. But sigma m was this, sigma xx, yy, zz divided by 3. So we get here 3 of these, and so 3 times 3 gets 1. Of course, these are sigma xx, yy, zz, but I have written it in different forms. This is correct also. So all of these cancel out. So we showed for J1 that is equal to 0. J1 is equal to 0 in here. So only we will have s to the power of 3, J2s, and minus J3. So if this is so, what is the value of J2? Similar to this, we can find the value of J2, like here. See, J2 is this parenthesis. Instead of sigma, we put s, Sxx, Syy like that, because it's in terms of s. So we are going to show this by using this expression. So here sigma xx is, Sxx is sigma xx minus sigma m. Okay, Syy is sigma yy minus sigma m, and similarly we write down all of these. Obviously, these don't have any components for the hydrostatic pressure because I is not equal to j, and therefore delta ij is 0. So we would have only sigma ij, which is s xy, syz, szy, zx. Here, of course, to the power of 2, all of them. Therefore, if we substitute these, obviously sigma xx is equal to sigma xy, because this delta is 0. So if we substitute all of these and multiply them out, you can see from here that we get sigma xx, sigma yy, sigma yy, sigma zz, sigma zz, sigma xx, which are the same as these, and this minus sigma xx etc. is this one. So that's I. That's I2. Okay, this is I2. So here, a third of 3I2, we get I2. What about the rest of the multiplications here? We have sigma x times sigma m and sigma y times sigma m. Sigma y times sigma m, sigma z, etc. So we will have 2 sigma m times sigma x space of sigma y, sigma z, of course with minus sign, and we will have also sigma m to the power of 2 here, sigma m to the power of 2, sigma m to the power of 2. But sigma m to the power of 2, of course, is this I1 over 3, so that would be I1 over 9. But we have 3 of these, so we get I1 over 3, and we get I1 squared, of course, because these are squared, and we will have, and the other terms also, we get the I1 squared, and subtract from each other, we get a third of I1 squared plus 3I2. You can write this yourself in longhand and see if you get that. Okay? So, also, J3 is equal to that. J3 is, instead of sigma, put S, Sxx, Syy, etc. And use this one again here. For Sxx, we put sigma x, sigma minus sigma m. For sigma yy, we put sigma yy minus sigma m, etc. If you put this, substitute for all of these from here, then you will, of course, this tau yz to the power of 2 is also s, but because it's equal to sigma yz, I have written here tau. It's the same thing as s yz, the same thing as sigma yz, and the same thing as tau yz. Okay, so I have used different notations in different equations so that you get used to it, and you would understand that these are the same. So this eventually, if you write it down in longhand, you will get I3 plus 1/3 of I1, I2 plus 2 over 27, I1 to the power of 3, and then you can write this like this, because J1 is 0, so you get S to the power of 3, J2 S minus J3